This research project centers around computing far-field gravitational wave signals. To provide context for this problem, we start by looking at black holes. A binary black hole system involves two black holes and another galaxy orbiting around each other and colliding. Their interaction results in gravitational waves. The main question we hope to answer is, what do these gravitational waves look like? Gravitational waves can be described as oscillating distortions in the geometry of spacetime that travel at the speed of light. The importance of studying these waves is that the origin, evolution, and populations of black holes and neutron stars can be uniquely probed with gravitational waves. Through studying gravitational waves, we can learn things about the black holes, such as their mass and spin. One important property of gravitational waves is that they barely interact with the matter they pass through as they propagate through space. This property allows us to learn things about a universe that we cannot see or understand due to studying other types of waves, such as electromagnetic waves. The main objective of this project is to find a way to accurately propagate gravitational wave signals over large distances. All numerical simulations of gravitational waves put the progenitor of gravitational waves in a box by truncating the problem to being only close to the black holes themselves. Through a technique we call gravitational wave kernel propagation, we can teleport or propagate a gravitational wave signal recorded at a distance r1, which can be described as the boundary of this artificial box, to a radius r2, or the location of gravitational wave detectors, effectively infinity. This is accomplished using a Python module that implements an Adams-Bashforth method for solving the relevant ordinary differential equations describing the teleportation procedure. As for the teleportation procedure, in order to get the signal at r2 equals infinity, we first need the signal at r1. This equation shows the relationship between the time domain and the frequency domain. If the given signal is in the time domain, we take the Laplace transform of it to get the signal in the frequency domain. The second thing that we need is a kernel. This kernel can either be given in the time domain, which can be seen in the first equation, or in the frequency domain, which can be seen in the second equation. The kernel is then applied to the signal at r1 to get the signal at r2. This is done in the frequency domain by multiplying the kernel by the outgoing signal at r1 and then adding that result to the outgoing signal at r1. This is the equation of the kernel in the time domain. In this equation, A sub Lk represents the residues, and B sub Lk represents the poles that define the kernel. These poles and residues are found through a written Python function that is a part of a teleportation module. They are then used to find the teleported signal. The Adams-Bashforth method of orders 1, 2, 3, and 4 for solving ordinary differential equations is used to teleport the signal at r1 to r2. The teleportation procedure was originally only done in the time domain. However, there are some drawbacks to this. First, the poles and residues needed for the time domain kernel can be difficult to compute. Additionally, the kernel and teleportation procedure is naturally in the Laplace frequency domain. By sticking to the frequency domain, there are no extra steps of going to the time domain. Additionally, we will be able to get and use more values for r. Therefore, we now turn our focus to the teleportation procedure in the frequency domain. This equation represents the kernel in the frequency domain. We created a Python function implementing the bilateral Laplace transformation. A main component of this written function is NumPy's fast Fourier transform routine, which implements the discrete Fourier transform. This function inputs a function evaluated at a discrete uniform time grid, the distance between times, and the array of times. It outputs the function in terms of frequency, as well as both complex and non-complex frequencies. In order to find the signal at r2, we first compute the exact frequency domain solution for the outgoing solution at infinity. This is done by taking the Laplace transformation of the signal in the time domain at r equals infinity. We then compute the Laplace transformation to find the frequency domain outgoing signal at r1. This is accomplished by taking the Laplace transform of the signal at r1 in the time domain. Finally, we find the frequency domain signal at infinity using the frequency domain kernel and the exact signal at R1. In our case, R1 equals 10, R2 equals infinity, and L equals 2. The results of this process of teleportation with numerically generated frequency is seen in the plot on the left. The lines representing the exact and teleported signals at infinity are overlapping. It was found that the exact and teleported far-field solution agreed to 15 relative digits of precision. In conclusion, we have developed Python code to carry out signal teleportation in the frequency domain. We have also verified its correctness on exact solutions. In the future, we will work to apply the Laplace frequency domain teleportation to gravitational wave signals. Thank you.